damos inicio al tercer y último día de Merelec ProCom Digital Week. En las conferencias del día de hoy hablaremos sobre la generación de pronósticos que desempeñan un papel relevante en la generación y comercialización de la energía, sobre todo debido a la continua expansión de las energías renovables. Para ello necesitamos herramientas, métodos y datos que nos permitan generar modelos útiles. Demos inicio.
La digitalización de la energía está transformando nuestra realidad a un paso acelerado. Descubre cómo la optimización y la generación de pronósticos ofrecen soluciones a los grandes retos de la industria energética en el evento Merelec ProCom Digital Week. 3 días para discutir soluciones de alto impacto económico con un equipo de expertos de Europa y Latinoamérica. Este 24, 25 y 26 de noviembre te esperamos en Merelec ProCom Digital Week, el futuro de la energía en Latinoamérica hoy.
En el sector energético, la generación de pronósticos juega un papel fundamental, ya sea que hablemos de consumo y demanda, generación de energía o precios spot en mercados intradiarios y de día en adelanto. Con esto en mente, damos inicio con la primera conferencia que lleva por nombre Mejores prácticas para redes inteligentes, pronóstico de demanda y niveles de generación distribuida. Conozcamos a nuestro ponente. Esta conferencia marca el punto de partida para hablar sobre pronósticos a lo largo de este día. Damos inicio. Bienvenido, Ingo.
Ok, bienvenidos, bienvenidas. Yo soy Ingo y soy de la empresa ProCom. Espero todos y todas estén bien, pero yo no hablo español, por eso comenzamos en inglés. Okay, so yeah, welcome to everybody. Today we are speaking a little bit about best practice for smart grids, and especially the role of load forecasting in distributed generation nets and on a distribution level. So the whole presentation, it's more about, okay, where we are coming from, what is the history, what will be the future, why is it the future, and what are the solutions, and what challenges do we have, and why is forecasting so important in that role. Last but not least, we also have a small Q&A session afterwards, and I will be part of that. So if you have any questions, write them down, raise your hands, and we will come to that after the whole presentation. Thank you very much for that. And yes, so let's dive in. The whole power grid, the old one, is separated into several layers. And here today, we are more focused on, let me show it here. We also have a laser pointer for that. We are mostly focusing on the lower levels, because on the higher levels, there are not so many changes and the challenges appear exactly at that level we are talking about. So just for clarification, the old grid layers are separated in the high voltage grid, where we have the overland transmission over very, very large distances. Then on a lower level, we have transformer stations and so on, which will bring the power to a lower voltage level. So then we have the medium voltage layer, whereas, for instance, windmills are providing power to the layer. We will see that later in another diagram. And last but not least, there are also transformers, which are on the low voltage level. And as you see in the old power grid generation, we are coming from that high voltage layer, will be transformed down to the other one in only one direction. So it's we also call it unidirectional. So that's the old-fashioned system, and we have an automated communication channels only on the highest level, where we want to keep in an automated way the net load stable and take care of this. And all the other ones we are not doing that, but this needs to be changed in the future. Then we automatically are speaking about our smart grids, but the question here is, what makes a power grid smart at the end of the day? So as said, the old-fashioned way, we have unidirectional power flows and information flows. That was on the highest level only. And in the new way, you see we have a lot of new actors in that grid structure, and the whole structure, also the structuring of the information flow, has been changed. So we have a lot of wind power plants which are generating power, which are not on the highest level power level. They are feeding the medium voltage grid. So we have a transmission from this one to the higher one. Before the old days, it was only the other way around. We are also mixing the power from the higher voltage then down to the low voltage ones. And there we also have private households more and more establishing photovoltaic assets on their roofs. We have small cogeneration in some industry areas and so on, which are also feeding the power net on the low voltage level. And we also have storages at some other apartments. Their storage are also power, maybe for their own electric vehicle, but they could also use it to feed the net if power is needed and the prices are perfect for them. And to get all these things automatically done, are a new whole system of monitoring the generation, the load, and the whole grid management needs to be done. In the former days, this was mainly needed for the highest level of the power transmission. There we need this one, but the more and more players in the market and also in the whole power grid, the more it is also needed on the lowest level. So the complexity increases, and we have a lot of direction of information flow, power flow, and so we are also saying, okay, that's our distributed power generation there. Yeah, just a little bit larger, the same screen of the new one. So what does it mean in general? So we have a lot of new competitors in our new smart grid. So we have a lot of new assets raising up for providing or generating power in this one. So we are speaking about biomass generation of power. That comes a lot of, if you're looking on the land side, a lot of people have, they are working on the countryside, just raising their plants, and later on, and then at the end of the day, they are also have, okay, what can we do with the rest of this? We could invest in biomass power plants, and we can power up the maybe our own facilities and so on. Or we also will still have conventional power stations. We have a lot of private new photovoltaic generation. We have hydropower, and last but not least, and this is the largest part, for example, in Germany, we have a lot of wind power and increasing amount of wind power in the whole net. So what does it mean? Especially for the grid, that means we have not a problem. Let's call it a challenge. We have the challenge to transmit the whole power from one location to the other one, because the wind power is generated at locations where we have a lot of wind. That makes sense. Also, when we are speaking about biomass, nobody wants to transport all the in general the biomass from location A to B over hundreds of kilometers. So we are generating at the location where the workers are doing all their normal work. So there's the biomass power plant. So, and then we are connecting all together on the power grid, and we need to manage the energy flow in that grid. And here, the new smart meters are becoming more and more important for exactly this one. So we have to measure the power flow, and we have to make sure that we are not that we have stable running power net. So in general, what we need to do there is we have to increase the building of a new infrastructure, or we have to upgrade our infrastructure. That means especially the power net, and this needs to be done in parallel to establishing new generation plants. So one cannot be done without the other. So these needs to be done in parallel. So, but we also have some more benefits from it. So on the consumption side, so for the households, industry, and also for the trading, can also say it's here everyone who is consuming power, who because the smart grids are offering, okay, we can say we have a prediction of some power production in the near future. Maybe we can connect some consuming factors in our household. Let's say the dishwasher or the washing machine for your clothes. So you say, okay, there's a time window where we can put them on, maybe, which is even cheaper for us to consume the power in that time window, because we don't care about when it's running. I just need to have it run during night, for example, or especially when you want to load your electric vehicle. So this can be considered, and this is a benefit which comes for the customer at the end of the day when we have this smart grid enabled for them. Especially also storages are becoming more and more important then, especially when we are talking about the hard, predictable, or not controllable power from wind and also from solar. When they are feeding the net and the load, so we cannot use the power, this power needs to be stored. Otherwise, we are overloading the net, and this could also have a lot of problems. So this needs to be avoided. So overall, all these players are playing a very, very important roles when it comes to power grids of the future, the smart grids. So some other examples here is how could it look like in the future. So over a time window, we have time frames where we have more power or we have less power, and how can we compete with them? So in the phases where we have not enough power, we have to ramp up our gas turbines or biogas cogen generators, or we have to force the industry to shift their production at the very end, maybe, so that the demand on power goes down. We also have our let's combine them all together as storage technology. So you can use your own battery at home to charge it. We could also charge our electric vehicles, which at the end, it's also just a battery with some tires on it. So we can also unload it on the streets and so on. But also another storage technique could be power to heat system. So we could feed the heating net just with power if we have enough one. Or we could export power or use any other technique. For instance, not feeding the heat net, we could also feed the gas net. Those are also ideas what you can do there. It's just use electrolyzers to make hydrogen, or methane, which is nothing else than natural gas. And which also was working in the past, we could export or import, just demand. It's just depends on which side we are at the moment. If we have too much, or yeah, if we have too much power, or on the other side too less power. Okay. Yeah. In detail, what does it mean? We have seen before the old power net has just one direction. So we are coming from a higher level, and we only have transformers in one direction, that we are transforming the power from the mid layer to the lowest layers, and we are transforming it from 110 kilovolt to 20 kilovolt, and for our households later on to 0.4 kilovolt. That's the old historical way. So you can say it's single protectors. We have no automation, no really communication between each member of the net, and this needs to be increased. So we need a second line of communication between all the members of that net. That means consumers and also the generators, and just to have an automated, stable system. Because what was working before only on the highest layer now needs also to be working on the lowest level as well. So just as an example, once again, is a generation now appears on the lowest level, and this power needs to be transformed if we combine them all together, maybe to a larger virtual power plant. Then we also want to transport this power later on the higher voltage levels to another location. Technically, this needs to be done, but normally just to reduce the loss of power on these transformation stations. So first, we want to use, of course, the power at the same level. That reduces the power losses, but we will face times where we produce more or less, so we have to use these transformations and to distribute all our power to the other levels. So it's getting more complex, but also more interesting, and we also have the chances of having new jobs and also new challenges we have to tackle there. So, but what are the tasks, or what are the benefits from the whole system? Is here we say we have I would say a single direction of energy flow, or we can also say it's a radio system, and there are smart grids. It's more like a meshed system, so everyone is connected in any direction to the other one. We need some automation in that net, so to control ourselves, just to have the net running stable. So we have to define, okay, we need some controllability on some parts. Unfortunately, wind power, solar is normally not controllable. So if there's sun, we will generate power, and we have to deal with that. But there are some like storages and also electronic vehicles, and also on the consumption side, we have definitely some ways to control our machines and so on. To make it this possible, we need a bidirectional communications between these not competitors, partners and members of the net. And this is, has to be done. So the challenge here is everything needs to be included step by step, of course. But the best working of this is when we install a lot of photovoltaic, for example, and then also in parallel already have established energy storage facilities. So that we can, if we are producing more power than we need, we can store this one. If the load on the net is already been fed, and then we can also store this to be used later on if we can't produce the power, for example, if it's night or so. So, and to make this possible, to have an idea when it's the time to store power, or when it's the time to take out the power from the storage, it's necessary to know when these times arise. So, and here the necessity of having forecasts exactly for this one is given, especially also for wind power, because for the German net, as I said before, the amount of wind power generation increases over time, on and on. And we see a lot of wind coming through this one, and we have to deal with that. Not only when it's already there, we have to know in advance, a couple of hours before when we have the. So it's necessary to have good forecasts, especially on every part of that layer, and that's it about. So the idea comes directly from the reorganization of the generation of power. So we have a lot of photovoltaic storages and wind power in there, and then automatically we know, okay, we need those forecasts there just to deal with that, to keep the power net stable at the end of the day. So just to show you something with some numbers, we can look on the diagram on the right side is the power generation 2018. It was in Germany around about 460 terawatt hours were produced from controllable power generation. That includes coal, natural gas, some others, biomass, nuclear power, and hydro. But which is not really controllable is photovoltaic and wind, which has a lower part, but this part it's getting more and more important, and the amount of controllable power shrinks down, and this makes or is the main conclusion or the main challenge we have to deal with. So for that part, we are producing more and more power. We need to establish like stable nets and in combination with a lot of storages. So it's mandatory to have really good measurements of these uncontrollable power output, and that also includes option. We say, okay, that should be optional, but measured values from the other generators are also important, because when we know, the more we know, the better we can create forecasts. As an example, we can analyze the whole structure every time. This also needs to be done later on in a semi-automated way or in a full automated way. We then can separate the forecast into the feeding part of the net of power and also on the consumption part. So that means, okay, we have the power net or power grid electricity plus the feeding forecast. We can generate somehow a synthetic consumption later on. If we have the synthetic consumption in that way forecasted, we could also do it in some other ways and combine this to a comprehensive forecast from several models. And we say, okay, we have now overall stable forecast of the consumption. That means also the net load which is there, and we can then subtract the feeding forecast, which leads then to the net electricity generation forecast. So this just as an example how it could go on in a very abstract way. And the big challenge then later on is this needs to be done automatically in the background all the time, because we are establishing new generators in the net. They're coming to it, or they will say, okay, this is not working anymore, like a windmill, it's out of order right now, then we have to delete it from the whole forecasting system. So it's getting more and more dynamically, and this needs to be tackled in some way. I have a lot of pictures today, but yeah, so how could possibly a smart grid or the whole power grid look like in the future? So I already said we have a lot of new ways to generate power. Just let's start on the left side. The more common ones are offshore and onshore wind parks. They have, as we have seen in the last slide, becoming a very important role of the renewable energy strategy, because they have the highest impact on the power production. And this will compete, of course, with the fossil power plants, and this goes then on the we have seen it on the first slides on the medium power level. And to control that, we have also a pumped hydropower stations. We could also use gas storages with power to gas units, and we have several consumption stations here. We could heating nets, or we could also use the cooling nets. We have also biomass generation, gas stations, and at the end, this goes then also to our private customers, which are here using gas, heat, or maybe also some cooling. So here cooling and heat had the same color. And as you can see, everything is somehow always connected to each other, and this needs to be maintained at the end of the day. So, and to get this monitored, we always taking part on more likely now in that area here. We see here we have, of course, on the higher level, on the higher layer, we also have a control center, but here we are more likely speaking about that microgrid controller. It's in general, you can say, okay, this is somehow similar, just on a higher scaling level here. But here on the lower ones, we are speaking about these private wind and solar farms. The smaller ones, other generators, it could also be some cogeneration or smaller biomass and so on. So all in all, we then call it more the decentralized regional power production. Back in the days, we had only the large nuclear, coal, and gas-fired power plants, where we had one big block which is producing enough power for a whole city, for example. And now this is changing to a lot of smaller units we need to get managed. So, and the main driver of this new change is that we want a transition to more renewable power, and this is then defines at the end of the day. So it's not only one technique. So the technique of all the other techniques we have here in the renewable energy sector defines the whole backbone of our new power supply. And this is definitely different from the old way. So yeah, this needs to be done, and therefore that's the big remark, or the large conclusion, and also the consent that we need for a lot of really good forecasts for these techniques and for any small location. And that's a big challenge here. So yeah, how would we do that? So we are at ProCom, we also provide several software to tackle this one. There is, for instance, our tool, the Beaufort, which will then have a transition to a cloud-based system later on. And we are also establishing another cloud-based system. It's a Clover, which is the IoT platform for plans and also some other machine and monitoring tools and for controlling as well. But first of all, just dive into a forecasting system. So what we have is a tool where we have a lot of several techniques to combine with each other. So we have on we're providing all our data in time series. We can combine them and build several kinds of forecasts. We can also analyze measured data there and create new forecasts depending on this one. There we can use several methods. Okay, these are the primitives ones, so we can also feed with low profiles, but the more interesting ones are then artificial neural networks, Serimax algorithms, and or we could also use multivariate polynomial regressions. It just depends on what kind of forecast you want to create there. So, and this is part of our Beaufort data hub. So here we just have seen that part of the Beaufort forecast, which consists on our time series management. We have several connectors to other systems, and together we could also use the optimization, but here we are now focusing on the Beaufort forecast, which will then go to or we will now transform it to a cloud-based system, which is then going to our new platform where you can have access later on via a web browser. So it's not necessary to have an on-site installation anymore, so you can configure and also customize everything there. So, and we still have automation, digitalization, of course, secured connectivity there. We can analyze all the data in the time series and build up predictions, or yeah, of course, forecast then. And if necessary, we can combine this also with some state-of-the-art optimization systems there. And last but not least, if we you also want to connect the system also to your machines you're running, and therefore we have established, or we also have the IoT platform. It's hosted by it's a Clover system, which is also used in on other machines and techniques and units we already have. So, and this could look like later on it's a whole landscape how it's working. So we have our assets running; those are communicating with the Clover system. It could be analog or also digital. They are sending signals to a gateway, which is then technically connected to the cloud system. And here we are using an MQTT interface, and the same interface is also communicating with our optimization and also forecasting system, which runs all the models, and we are sending back our information to our machines, how they should run in the future. To keep this running, those forecasts, of course, or obviously needs to be very accurate. And the benefit is now you can have access to it via your mobile and also just via web browser. So you can look on actual values. You can also have a look on your forecast as well, what's going on there. So this is the way how it should go in the future as well in general. In detail, how does it look like? You could also, of course, if you want, have access to the Clever system, which is communicating with a lot of several standard systems as well. And here we are now more focused on exactly this part here, that we have a system set up which is communicating with sensors. As said before, we this whole system comes more from our other business units, where we have links to several cutting systems. So the machines are working then on the signals we are giving them over this cloud, and this helps and speeds up things if it's then implemented correctly there. So yeah, just as an example, how could it look like? You can open your browser. There are also plenty of other examples out there. So it's necessary to create dashboards for progress. Of course, if you have a photovoltaic unit, you are not necessarily want to see a hydro power plant there. So could be connected to a webcam there. So you have a look on that. Oh, it's very sunny outside. Why is my power plant not, for example, your photovoltaic unit not running? So there might be an error. So we could also check it by that. And you can, with more simple traffic light systems and whatever it's necessary can be published in a dashboard for like this one. Or there are also some other dashboards out there where you can have a look on the install or the productivity for some other windmills out there. So here we have a screenshot from that inner serve also added there. And of course, to get this running, you need a lot of new parts in your whole system. So these in general, or in particular, these are then signal converters, which is then getting this done from that analog and digital sensors to our interfaces. So, and all together, we can say that's the whole smart kit we are providing. And to tackle all these challenges we have with these forecasts integrated in our new virtual power plants or in our small distributed networks, we have to provide. And that's how it could look like. Yeah. So if you have any questions so far, we can have in the Q&A session a lot of time to discuss it, or maybe you have some other ideas how to tackle this, but this is our way, how we want to go in the future, how we want to solve all these challenges. And yeah, I'm really interested to hear what's your opinion about it and how we can help there. Thank you for your time.